The goal of this video is to teach you how to use a simple yet powerful mathematical tool to solve certain complex problems. To introduce one of these problems, we'll start from some known results. This cylinder has been filled with water. There are 3 taps that allow it to be emptied, and when they are opened, the water will flow out of each at different speeds, following Torricelli's law. Torricelli discovered that this exit speed is the same as the speed a body would reach in free fall from a height h equal to the distance between the tap and the liquid level. The draining speed, meaning the ratio between the volume delta V of water that comes out and the time delta t it takes, equals the product of the cross-sectional area S of the tap's hole and the speed at which the water exits. Combining these 2 pieces of information, the draining speed can be written as the product of the section and the square root of 2gh. Let's plug some data to test this formula. The cross-sectional area S is 20 square millimeters. G is the gravitational acceleration, and we will keep the height of the water column above the tap constant at 28 centimeters. If we didn't refill the column, h would vary over time, and the formula would turn out into a differential equation with separable variables, but we prefer to keep the experiment simple. We find that about 47 milliliters of water should come out of this cylinder every second. If everything is correct, in 20 seconds, about 930 milliliters of water should flow out. Torricelli's law applies to ideal, non-viscous, incompressible fluids, and in this sense, water is an excellent candidate. It's also important that the hole is small compared to the container, which is true in our case. Let's look at the result. In 20 seconds, we collected an amount of water very close to 930 milliliters, with a margin of error that by eye is no more than 5%. So, what is one of the complex problems we will learn to solve today? Follow me closely, because this is really worth it. Imagine that the container is emptied through a set of horizontal tubes with different diameters intersecting each other to form a network of pipes. The junctions and the branches allow the water to pass from one part to another, speeding up or slowing down the flow. What is the draining speed now? The answer will be so straightforward you won't believe it, and to convince you, I'll have to show you that it really works. So let's build a model. You can use a plastic cup or a bottle as the container, some straws as pipes, and small jars as junction points between the straws. Keep the straws horizontal and insert them into the upper part of the jars. In fact, the presence of air in the junction points may greatly affect the results. Instead of using straws of different diameters, you can connect the jars with 2 or more straws. You'll also need a bit of glue to make everything watertight. When the work is complete, the model will look something like this, but feel free to customize it. At this point, you might be wondering, what complex formula of hydraulic physics governs this system? Well, no physical formula. The pure and magical mathematics of graph theory will do the job. Everything starts from a graph, a set of points that can be connected or not in pairs by a line. On this graph, we choose 2 special points and call them S and T. Moreover, we assign to each line a non-negative number called the capacity of that line. In practice, the points of the graph represent the junction nodes, the lines represent the straws that connect them, and the capacities represent the number of straws between 2 nodes. Point S is the water source. Point T is the water's target, the container that will collect the outgoing water. Beyond the experiment, such a graph is an abstract mathematical object with applications in many contexts: transport of goods, movement of people or cars, electrical networks, even the circulation of information. Given a graph with a source, a target, and assigned line capacities, we can mathematically define what a flow is. A flow is the assignment to each line of a direction and a numerical value between 0 and the capacity of that line. This value represents the amount of water that flows in that direction. If it is 0, there is no flow. As it increases, it indicates a greater flow until the tube is saturated, reaching its capacity. A flow must satisfy one condition. In every node, by the principle of conservation, the amount of water entering must equal the amount leaving, except for the source and the sink. In other words, for every point of the graph except S and T, the sum of incoming arrows must equal the sum of outgoing arrows. Given a flow f, we define its value as the sum of the values on the arrows leaving the source minus the sum of those entering it. Yes, flows with arrows entering the source are allowed too. So the flow value can be negative, as if the water were moving from the sink back toward the source. Don't worry, what matters to us is finding the flow with the maximum value, the one that transports the greatest quantity of material from S to T. So, here we have a flow with value equal to 4. Can we do better? Is it the maximum value of a flow in this graph? The answer is given by the max flow mean cut theorem, which states the maximum value of a flow equals the minimum capacity of a cut. Alright, but what is a cut? A cut T is a partition of the points of the graph into two groups, in such a way that the source is on one side and the target on the other. The capacity of the cut is just the sum of the capacities of the lines that connect points from the first group to those of the second. For a practical example, consider this cut. On one side, we have the blue points, including the source. On the other, the red ones, including the target. The lines connecting the blue points to the red ones are the lines of the cut. The sum of their capacities, equal to 7, is the capacity of the cut. There are many possible cuts, but the theorem states that the smallest possible capacity among all cuts corresponds to the maximum flow value in the graph. Think about it. Take any flow and any cut. Since the flow must go from the source to the target, and the source is among the blue points while the target is among the red, the material transported must necessarily cross the lines of the cut. So, at most, it can pass through an amount equal to the total capacity of the cut. Therefore, the value of the flow is less than or equal to the capacity of the cut. If we now take the maximum flow and the minimum cut, we get that the maximum flow value is less than or equal to the smallest possible capacity. The max flow mean cut theorem tells us that in fact they are equal. I won't go into the proof because Ford and Fulkerson, the two mathematicians that formulated the theorem, also devised an algorithm to compute the maximum flow. Let's look directly at their algorithm. We start from the given graph and split each line into two arrows to represent both possible flow directions. On each arrow, I wrote the capacity of the line, repeated on both directions. Now, look for any path from S to T and identify along this path the smallest capacity among those crossed. Suppose the path passes through capacities 3, 2, 2, 3, the smallest value is 2, we subtract this value from the capacities along the path and, careful, we add it to the arrows in the opposite direction. This last step is the key feature of the Ford-Fulkerson algorithm. If you forget it, you will be following another algorithm, called the greedy algorithm, which does not guarantee finding the maximal flow in the end. We repeat the process along new paths from S to T, avoiding arrows with zero residual capacity. To speed things up, it's convenient to choose paths that go through arrows with higher capacities. By continuing in this way, we'll eventually reach a point where no more paths can be found. This could be proved formally, but without going too technical, the continuous reduction of residual capacities inevitably leads to a separation of the graph into two groups, one containing S and one containing T, with the property that arrows connecting points from the first group to points of the second have zero residual capacity. This separation corresponds to a cut, in fact to the minimum cut. The capacity of this cut is by construction equal to the sum of the values of the paths used. The only thing left is to build the maximum flow by overlaying the paths used during the algorithm. In the example shown, the value of the maximum flow is 5, which is also equal to the capacity of the minimum cut. Now we can put everything together. To compute the draining speed, we take Torricelli's formula and replace the cross-sectional area S of the hole with the total section corresponding to the minimum cut of the pipe graph. The minimum cut, in fact, determines the maximum flow. In other words, instead of S, we must use the smallest possible sum of the tube cross-sections among all the cuts of the graph. In our example, where all straws have the same cross-section S node, the formula becomes K times S node times square root of 2GH, where K equal to 5 is the capacity of the minimum cut calculated earlier. So, even though the straw in the network starts with 7 outlets from the source and ends with 7 straws at the target, the outflow from our network will be just 5 times the outflow from a single straw. Moreover, the Ford-Fulkerson algorithm gave us the maximal flow, so we should know how the water will distribute through the tubes, right? Wrong. The algorithm gives us the correct maximum flow value, but there isn't just one possible flow with that value. There are many different flows that reach the same maximum value but distribute the water differently across the pipes. If you are curious to find out how to compute the actual water flow, the one that really happens in the model and that allows you to know how much water will come out of each pipe, let me know in the comments. It's a longer work, but if you're interested, we'll tackle it in a future video, always following our philosophy, solving complex problems with the simplest mathematics. What's left? Testing the formula. Notice it's not necessary to take all the measurements. In fact, since the minimum cut equals 5, we can just check that for the same height h, the draining speed of the network will be 5 times the draining speed of a single straw. I've filled the pipes in advance up to their level, and this is essential. We have used the conservation principle several times, but if the jars weren't full, the incoming water would accumulate in the nodes and wouldn't match the outgoing flow. In the same amount of time, we collect 22 milliliters of water from the single straw and almost 100 milliliters from the network. Not bad, but to get more accurate results, it's better to use shorter straws with larger diameter. I really recommend it since friction and turbulence tend to slow down the flow, especially in the network. If you enjoyed this video, leave a like and subscribe. That's the best way to keep the channel going. See you in the next video, and in the meantime, don't panic.